so start the recording. All right, so let's look at the P22 question, November 2021 P22. The easy questions, I'll just breeze through it. Okay, now for 1A, a unit may be stated with a prefix that represents a power of 10 multiple or submultiple. Complete table 1.1 to show the name and symbol of each prefix and the corresponding power of 10 multiple or submultiple. So what you have here is just a simple multiple submultiple question. You need to know the different values of the multiple and submultiple. So by now you should be able to know that kilo is 10 power 3, mega is 10 power 6, giga is 10 power 9, tera is 10 power 12. So if you go to submultiple, deci is 10 power minus 1, centi is 10 power minus 2, milli is 10 power minus 3, micro is 10 power minus 6, nano is 10 power minus 9, pico is 10 power minus 12. So all these values you need to know before you sit for your exam. Okay, so right now if you look at the table, what are some of the things that are missing? Tera T is 10 power 12. We already know from here. And then after that, when you look at the other row, you have submultiple 10 power minus 12. That belongs to pico with the symbol P. Okay, so this one is okay. Now in the following list, underline all the units that are SI base units. So the keyword here, it must be base units. Ampere is SI base unit. Meter is SI base unit. Coulomb is not SI base unit. Newton is not SI base units. You have 7 base quantities. The first one is mass, length. Second one is length. Third one is time. Fourth one is current. Fifth one is mass, length, time. The fifth one is temperature. Then after that, the sixth one is amount of substance. Seventh one is luminous intensity. These are your base quantities that you would have learned up to now. So all these are your base quantities, but when it comes to the units, mass is kg, length is meter, time is second, current is ampere, temperature is Kelvin, amount of substance is mole, luminous intensity is candela. Now for the 7th one, luminous intensity, this one is not really in your syllabus. We don't normally test you on that. You're really supposed to know up to the 6th one over here. Okay, right, so the SI base units are the units of your base quantities. So from here, we know we have ampere, we have meter. Coulomb and newtons are not in. Coulomb is for the quantity of charge, whereas newton is for the quantity of force. These are not the base quantities. So the units for these base quantities cannot be, we want the base units. So the units must be for the base quantities, which is the ones that you see here. Anything other than that, those are not applicable. Charge is not a base quantity, force is not a base quantity, so their units are not considered to be SI base units. All right, then after that, we looked at part C. The potential difference B between two ends of a uniform metal wire is given by this expression here, where D is diameter, I is current, L is the length, and rho is the resistivity of the wire. For a particular wire, the percentage uncertainties in the values of some of the above quantities are listed in this table here. So this one is percentage uncertainty. Whatever we have here is in terms of percentage uncertainty with a percentage sign there. The quantities listed in table 1.2 have values that are used to calculate rho as 4.1 times 10 power minus 7 ohm meter. For this value of rho, calculate the percentage uncertainty. Okay, so we want to find out the percentage uncertainty of rho, which is the resistivity. They want percentage uncertainty. So just to refresh your memory a little about uncertainties, if I have uncertainty plus minus delta rho, absolute uncertainty, delta rho, and then delta rho over rho, delta rho over rho times 100%. These are all known as different things. This is absolute uncertainty. Okay, this is absolute uncertainty. This is fractional uncertainty. This is percentage uncertainty. Okay, this is what we call as percentage uncertainty. All right. So depending on what they want, you will tend to change your expressions differently. So right now they want the percentage uncertainty for rho, meaning to say they want this form. Okay. So based on what we have, we want to find out rho, which is the resistivity. The given equation was V equals to 4 rho Li over pi d squared. You make rho the subject, you're going to get pi d squared V over 4 Li. Now from here, you would be able to get something like this, where we say that fractional uncertainty of rho is 2 times of fractional uncertainty of D plus fractional uncertainty of B plus fractional uncertainty of L plus fractional uncertainty of I. This pi and 4 here are ignored because they are constants, right? They don't have uncertainties. So usually that is one of the things that you just need to be aware of. Any constant you see, you just ignore it. And then there are a few rules when it comes to deducing the expression for uncertainties. If y is equals to a plus b or y is equals to a minus b, then you will get delta y equals to delta a plus delta b. If y is a times b, or y is equals to a divided by b, then what we'll get is fractional uncertainty of y is fractional uncertainty of a plus fractional uncertainty of b. So there will be another variations to this also. Sometimes when we say that y is a power m, we say that this one is a power m times with b power n, or y is a power m divided by b power n. In these cases, fractional uncertainty of y is m times of fractional uncertainty of a plus n times of fractional uncertainty of b. Okay, so what you have here is very similar to this. That's why we do it like this. If you notice there's any power, you tend to bring them down. Okay, yeah, one thing to note here also will be this. Ignore any negative in the powers. What we mean by this is that sometimes you may get an expression that looks like this, where I tell you that, say maybe y is a power 3, b power negative 2. In our case, this one will just be fractional uncertainty of y, 3 times fractional uncertainty of a, plus 2 times fractional uncertainty of b. The negative sign here will just be ignored. Okay. Although we look at this one, the general equation, it seems that we are bringing down the power. But when it comes to bringing down the power, if your power has a negative, this one you have to ignore it. Okay. The reason is because, why do we ignore negative is because uncertainties can only add up with more measurements taken, with more different measurements taken, with more different measurements taken. Okay, the more things you try to measure, each measurements actually have their own errors. So if you measure more and more things, your errors are only going to add up. They by right will not subtract. You will not have a negative sign. If you have a negative sign, that means that the more things you measure, the less errors you have. That one does not make sense, because if let's say you measure 3 different things to get a final value, each of those 3 different things have their own errors. They are only going to add up to your final value. Okay, so they must never be subtracted, only added up. That's why ignore any negative sign. Okay, so now that you have this expression here, all you just need to do is that you just need to add in the values, sum in the values. In my case, I already know all the percentage uncertainties of the values given here. If I wanted to get the fractional uncertainty for this table, all I just need to do is that I divide by 100. So this one is 0.03, 0.02, 0.025, 0.035. Okay, whatever I have here was actually all in fractional uncertainty. So all you just need to do is you sub those values in. You're gonna get something like this. So here you're gonna get the fractional uncertainty of resistivity as 0.14. But since they want the percentage uncertainty, you just multiply by 100%, you're gonna get 14%. This form here is fractional uncertainty. You want the percentage uncertainty. When it comes to fractional uncertainty changing to percentage uncertainty, this one you multiply by 100%. But when it comes to percentage uncertainty back to fractional uncertainty, this one you divide by 100%. Okay, so that's all there is to it. And then after that, the last thing they'll ask you to do is to find out the absolute uncertainty. Okay, to find the absolute uncertainty, this one probably would be very straightforward. Since you know that the percentage uncertainty is 14%, if you try to write out the full equation, delta rho over rho times 100% will be 14%. So you want the absolute uncertainty, you want this one. This one is your absolute uncertainty. So you need to sum in the values for everything else inside to get this delta rho. You already know the resistivity as here. They already told you the value. You already know the value of percentage uncertainty as 14%. So you know all this already. So just sum everything in. Delta rho is equals to 0.14 times 4.1 times 10 power minus 7. You eventually gonna get your absolute uncertainty as this value. Okay. Yeah, one thing that I should mention to you here is that when it comes to finding the values of absolute uncertainty must always be at 1 SF only. Okay, but when it comes to fractional uncertainty or percentage uncertainty, it can be 2 or 3 SF. Okay, so absolute uncertainty, just be careful. Usually we only want it at 1 SF. So here you notice that I got it as 5.74 times 10 power minus 8. I don't leave it as 2, I don't leave it as 3. I tend to leave it as 1 because absolute uncertainty tends to be at 1 SF only. This is the special case when it comes to absolute uncertainty. Okay, last time I mentioned to you guys before that final answer usually must be minimum 2, maximum 3, right? There are some exceptions. If you have absolute uncertainty, most of the time you have to put it at 1. Okay, right, so this one is okay. This one is question 1. Then we move on to another part. Okay, right. This particular question, question 2 onwards, right? Question 2 onwards, when it comes to question 2, question 2 is on electric field. Electric field from 2022 onwards, which is the year that you are currently sitting for, is no longer in AS. Okay, it's no longer in AS. It's now combined with A2 instead. So this question, there are some parts of it that you cannot really do, all right? But there are some parts that are actually still related to what we have. Wait on. Okay, maybe we skip this one first, right? Maybe we skip this one first because this one relates to, because if I explain this one probably will take some time, may not be relevant. Okay, so we skip question 2 first because this one has something to do with electric field, but let me see whether we add anything. Okay, no, we skip this one first. No, we skip this one. All right, let's just look at question 3. All right, okay, question 3, define power. Power we already know is rate of work done or work done over time taken. So equation wise we know is this, but be careful not to write it in equation form like this. If you really want to write it in equation form, you write it as this. Power is equals to work done over time taken. I mentioned to you guys before that if you want to define any particular physical quantity, you want to write the equation, please write it out in words like this. If you write it out in symbols like this, the symbols must be defined. If you just write this equation but without defining the symbols, the examiners will not accept that because they don't know what the symbols mean. They want the symbols to be specifically defined. But if you do that, you might as well just write this straight. Okay. So you're not writing it in equation form, you can actually just write it in word form like this, no? Rate of work done. That's all there is to this. Okay, now you look at part B. You have a car of mass 1,700 kg that moves in a straight line along a slope that is at an angle of theta to the horizontal. The car moves at constant velocity for a distance of 25 meters from point A to B. Air resistance and friction provide a total resistive force of 440 Newton that opposes the motion of the car. For the motion of the car from A to B, state the change in the kinetic energy. Okay, the keyword here was, what is the change in kinetic energy? What you do know here is that there's a keyword. The car moves at constant velocity. All right. So from here all the way to here, it was moving at constant velocity. So right now, your question is asking for change in kinetic energy. But since your velocity remains constant in the first place, there's no change in kinetic energy. There is kinetic energy here, just that there's no change. It could be that maybe at point A, KE was 1,000 joules. At point B, KE is also 1,000 joules. From here to here, KE change is 0. Okay, but you have KEs on both these points here simply because you have speed. Just that, but the only thing is that since the speed did not change, your KE did not change. It remains constant. So no KE change. Then the next one you want to do is calculate the work done against total resistive force. So work done against total resistive force, another keyword here that you would have seen is this. Resistive force is 440 Newton. That is opposing the motion of your car. So you want to find out the work done against your resistive force, we know it's W equals to Fs. But the S must be distance move along direction of the force. So we are talking about this distance here. Okay, our resistive force is 440 Newton opposing the motion of your car, but in terms of the distance that has been moved, it is this line here, which is 25 meter. So you just sub that in, you're going to get the answer as 1.1 times 10 power 4 joules. All right. Okay, so this one should be okay, nothing much to it. Then there were some other things here also. All right, then you look at part C. The movement of the car in B from A to B causes its GPE to increase by 4.8 times 10 power 4 joules. Calculate the increase in vertical height of the car for its movement from A to B. So, some wordings here to note. GPE increase by 4.8 times 10 power 4 joules. Then calculate the increase in vertical height. So this one just use energy equation. Change in GP is mgh, where h is always the vertical distance move. It's always the vertical distance that has been moved. All right, which is also in our case vertical height h now. So just sub in the value 4.8 times 10 power 4. Your mass is 1700. Your gravitational acceleration is 9.81. You will eventually get h as 2.88 meter. Your mass is 1700 kg is already written there, so just put it as it is and you should be fine. Okay, then the next one that I want you to find is to find out the angle theta. The next thing they want you to find is the angle theta. Angle theta here, this one you need to use triangle. If I draw for you the diagram that you have just now, if I draw for you a simplified diagram for the car, when you move from A to B, you can imagine that there's a triangle here, like this. This is the angle theta that you want to find. So right now, you actually already found out the height at some value. You already found out the diagonal length. You can actually use Pythagoras theorem. So this is the diagram that represents the right angle triangle that you ought to have. The diagonal length is 25 meter. The vertical length is 2.88. This is opposite over the hypotenuse. So this one will be sine theta h over s. 2.88 over 2.5. Upside that ratio, you're going to get 6.62 grams. So that one should be straightforward. Okay, so this one is okay. Then after that, you move to the last part. Last part is this. Okay. Now the engine of the car in B produces an output power of 1.7 times 10 power 4 watts to move the car along the slope. Find out the time taken for the car to move from A to B. Okay. So based on what we have here, we want to find out the time taken for car to move from A to B. Now, if we want to use energy conservation here, we can. If let's say we're talking about the car here, the car was over here right now. Just now, this one was at point A, and then it moved to point B. Okay. Now we know that the car has an engine. The car engine is the one that produces power to move your car from A to B. Now there are a few energy changes that could occur here. What we can say here is that in general, the work done goes into changing the GPE goes into changing the KE and also work done against friction. Okay, why do I know there is change in GPE? Because there is change in height. If I have change in KE, there is change in speed. If I work done against friction, there is resistive force or friction. But then right now you know that, so based on this, what you can understand from this equation is that whatever work that has been produced by your engine or whatever power that has been produced by your engine has been used to increase the GPE, increase the KE, as well as to do work against friction. Okay, so right now you can think of this as work done against work done by the engine is used to increase your GPE, used to increase your KE, as well as to do work against friction. But we also know one thing from the earlier part of the question just now, your car is at constant velocity. So if we know that this one is at constant velocity, this one was constant velocity, therefore change in KE is 0. So our resulting expression will just be this only, no? Whatever work that was done by your engine was used to overcome the resistive force as well as to increase your GPE. So both of this is something that you already found before. Your change in GPE you found in here, sorry, you can actually find it from here. They told you your GPE increased by 4.8 times 10 power 4. The work done against air resistance, sorry, work done against resistive force, you found it in the previous part, which was this one, 1.1 times 10 power 4. So really, all you just need to do is you sub in everything, 1.1 times 10 power 4, 4.8 times 10 power 4, giving you this, all right? But what you have here is power in watts. This one is in terms of work done, so it's not yet complete, all right? We know that power is work done over time, all right? So if power is 1.7 times 10 power 4 and work done is 5.9 times 10 power 4, it follows that we can find T. T would be 3.47 seconds, just like this, okay? So this one is the easiest one. There's a longer method for this. This one is where you try to use the velocity equals to displacement over time equation. And then after that, you need to find the velocity before that. But this is a longer method. So this one, if you have time, you can actually have a look at it. But I won't suggest you use this method because this one is actually longer. The most straightforward one would be what I showed here in pencil, because it makes use of the values that you have already calculated. The longer method here needs you to calculate some other stuff. Okay, so it's not something that is recommended. Okay, so this one is okay. Then we go to 4. Okay, 4 is on Doppler effect. This is the one that for some people is quite difficult. All right. So let's just read through this question first. Now, we tell you right now for question 4, a child sits on the ground next to a remote control toy car. At time t equals to 0, the car begins to move in a straight line directly away from the child. Okay, keyword here is that your car is moving away from the child. The variation with time of the velocity of the car along this line is as shown in figure 4.1. So this is your velocity time graph of the car as it's moving away from the child. You will notice some stuff here. This one, the car is speeding up. This part is speed constant. And then the last part here, you will notice you are slowing down. Okay, from here all the way to here, you're always still moving away from the child. At no point did you ever change your direction to move back towards the child. Okay, because you see all this is still positive velocity. So you're still moving in one direction only. Okay, that's what you can see from here. All right. So to illustrate what's happening here, you imagine that the child is here, and then the car is just moving away from the child. So at some part, it's speeding up. At some part, it's constant speed. And then at some part later on, it's slowing down. Okay, so that's what this graph is telling you. Okay, now from here, they tell you the car's horn is continuously sound. Okay, the car's horn is being used continuously so that it emits sound of frequency 925 Hz between 0 and 6 seconds. The speed of the sound in the air is 330 meters per second. For the question that follows, they ask you, describe qualitatively the variation in any of the frequency of sound heard by the child that was emitted from the car horn. This one is talking about your frequency observed. Okay, so what is the variation of the frequency observed by the child when the car was moving between 0 to 2 seconds? Okay, so what we do know is this. Last time in Doppler effect, this is what we mentioned to you, right? If say your source is moving towards observer, your observed frequency will be more than your source frequency. But on the other hand, if your source is moving away from observer, your observed frequency will be less than your source frequency. Okay, these were the two main conclusions that you would have learned from Doppler effect. You always see whether your source is moving towards or moving away. That will change your observed frequency to either being larger than or smaller than your source frequency. Okay, so right now, there was also another thing that I should also mention from here. Your frequency change, which is either an increase or decrease, depends on speed of the source. Okay, what we'll tell you here is that the higher the speed, the greater the change, and vice versa. So basically what you're supposed to know from here is that if you move at a higher speed, your change in frequency is going to be larger. Okay, the greater the change in observed frequency. Okay. Greater the change in observed frequency. All right. So if you have a source that's moving faster towards the source, so you have a source that's moving faster towards the observer, your frequency increase will be larger. if you have a source that's moving faster away from your observer, your frequency drop is going to be lower. This one was actually explained before in this part for waves. I mean, if you joined last time, I think you would have gone through the chapter for waves before, right? So this one here actually relates to this part in the notes, the last page of your notes for waves. Okay, that time I mentioned to you what happens when your source is speeding away from you or slowing down away from you or speeding towards you or slowing down towards you. So to summarize, this is what is happening. Okay, your frequency change, either increase or decrease, depends on your speed. If you're moving at higher speed, you're going to have a greater change in your frequency. So that change is either increase or decrease now, but it depends on whether you are moving towards or away from the observer in the first place. So let's look at this question right now. Because we know that in our case, the source is moving away from the observer, your observed frequency will always be lower than your source frequency. Okay. In other words, your frequency observed decreases. Okay, your frequency is decreasing. Okay, in other words, your frequency is decreasing. You know, let me just write it properly here. In other words, your frequency is decreasing. Frequency observed is decreasing. Okay, so that frequency decrease depends on your source speed. The higher your speed, the larger the frequency decrease, and vice versa. Okay, so if let's just say you try to visualize what's happening right now in the form of frequency observed versus time graph, this is what you're gonna get. This particular shape here. See, this part here represents you speeding up. Wait, let me just write it out. This part here represents you speeding up. This part here represents constant speed. Wait, let me just clear this thing away. This part here represents constant speed. And then this part here represents you slowing down. Okay. So you see, when I speed up, my frequency drop is increasing. When I am moving with constant speed, my frequency drop remains constant. But then when I slow down, my frequency drop decreases. Okay, that's what I can conclude from these stages. My observed frequency will always be less than my source frequency. You see over here, your observed frequency is always still less than your source frequency. Source frequency, you can just think of it as this x-axis over here. Okay, wait, now let me use a different color. You can just think of it as being the x-axis over here. Okay, this is your source frequency at, say, 925 hertz. Okay, so if you're speeding up, you are speeding up as you're moving away from the observer, your frequency observed will drop. Okay, but the drop will increase with time. But then after that, when you start to move with constant speed, you're still observing a frequency drop, but the drop is constant throughout. But then when you slow down, your frequency is still dropping, but it is decreasing with time. Okay, so based on what you can see from here, if you just look at the observed frequency itself, for the stages when you're speeding up, observed frequency drops. For the stages when you're moving with constant speed, your observed frequency remains constant. But for the stages when you're slowing down, your observed frequency increases. Okay, so right now the question is just specifically asking you for time 0 to 2 seconds, which is basically this one. So you notice that your frequency observed is decreasing. But then the next thing they'll ask you is, what about for 4 to 6 seconds, which is basically over here. You will notice that your observed frequency is increasing. Okay, so that's how you make sense of this. Why we say that the observed frequency decrease, why we say that the observed frequency increase. For both these cases, observed frequency is still less than the source frequency because you're still moving away from the observer. But the amount that has dropped, the amount that is less changes. Okay, right. So this is the difficult part about this question, but the subsequent parts should be quite easy. Okay, so now if you look at part B, we tell you that we want you to determine the frequency to 3 significant figures of the sound heard. Okay, determine the frequency to 3 significant figures of the sound heard by the child that was emitted from the car horn at time t equals to 3 seconds. They want you to find the observed frequency at t equals to 3. So since we know that your car is moving away, F naught will be VW over VW plus VS times Fs. So what you just need to do is this. At 3 seconds, find out what is the speed of your source. We already know the speed of the wave. If you just look at this one, the 338 meter per second, this one is the speed of our wave. The 925 here is the speed, frequency of our source. So at t equals to 3 seconds, over here, this is the speed of our source, which happens to be 12 meter per second, if you read the graph. Okay, so we know everything, we just sum everything, 338 over 338 plus 12, multiply with 925, this will be our observed frequency at 893 Hertz. Okay. So another thing to mention also when you're talking about Doppler effect for their equation, source moving towards the observer, you by now should remember this by heart. If it's moving towards observer, F naught will always be VW over VW minus VS times F naught. If source is moving away from the observer, it's F naught equals to VW over VW plus VS times F naught. Fs. Both are Fs, sorry. Okay, so this is the equation that you need to remember also correspondingly. All right, even if let's say you somehow forgotten about this, there's still some way to help you because if you look at the third page of your question paper, they have the Doppler effect equation, but it's written in a slightly different manner. This is your Doppler effect equation, the third page of your question paper. If let's say you need some validation on whether you have the correct form, you can always refer to the third page of your question paper. Okay, right. So we found out the observed frequency at t equals to 3 seconds. So this one is okay. Then we move on to the other part. This one here is something else. This one, they are asking you for part C, determine the time taken for sound emitted 4 seconds to travel to the child. Okay. So they want you to find out the time that's taken for sound emitted at t equals to 4 seconds to travel back to the child. So what is happening here is this. If you want to visualize what's happening, originally this is your child here, and then this is your car. This one was at t equals to 0 seconds. Then after that, we all know that the car has started moving. The car has started moving until such a point that it reaches t equals to 4 seconds. At t equals to 4 seconds, they want you to find out what is the time taken for the sound wave that's emitted by the car at this point back to the child? Sorry, this is 4 seconds, right? Okay, this is 4 seconds. So this one was at t equals to 0, t equals to 4. The car was here at t equals to 0. The car is now here at 4 seconds. Throughout that time, your car is emitting sound waves. Okay, the sound wave will propagate in all possible directions. It will go forwards as well as backwards now. All right, but what we're interested right now is that at this point here, your sound wave is being emitted. Your sound wave will travel back to the child. They want you to find out what is the time taken. Right? So when it concerns time taken and it concerns speed, we know the speed of the sound already as 338. You by now should at the very least have an idea that, oh, you're probably going to need to use this equation. V is equals to S over T. We want to find T. We know what is V, but we're still missing the time, the displacement, the distance moved. Now this one you can find. Okay, if we are able to find out what is the distance moved from here to here, and we know the speed as 338 meter per second, we can find the time. So where can we find out the distance that has actually been moved by the car? You can actually relate it to your velocity time graph here. If you look at your graph before this, this is the velocity time graph of the car as it has moved. So you make use of that information. The graph basically looks like this. This one was 2, this one was 4, this one was 6. The distance that has been moved by the car up to 4 seconds would actually be given by this area over here. That's why here I'm trying to find the displacement. It is half, is the area of a trapezium. So it's half 4 plus 2 times 12. This one was 12. This is 36 meters. Your car will need to travel, sorry, the sound wave will need to travel a distance of 36 meters back to the child. So you use V equals to S over T, 328 over 30 equals to 36 divided by T. T will be 0.107 seconds, just like this. All right, right? So this one is simple application of waves for Doppler effect. Okay, right. So this one is okay. Then I move on to part 5. Sorry, question 5. Okay, question 5 concerns stationary wave. Okay, so this one probably will be a good revision for the stationary wave chapters that we just done before. Okay, right now, if you look at question 5, we have a tube that is initially fully submerged in water. The axis of the tube is kept vertical as the tube is slowly raised out of the water. So from there, we mentioned to you that a loudspeaker producing sound of frequency 530 Hz is positioned at the open top end of the tube as it is raised. The water surface inside the tube is always level with the water surface outside the tube. Meaning to say this now, this is the water level inside the tube. These are the water level outside the tube. They are always level, means that they are always along the same line. Okay. From here, we also say that the speed of sound in the air column in the tube is 340 meters per second. That's what's happening over here. They're asking you to tell us right now, describe a way that a student, without requiring additional equipment, can detect when a stationary wave is formed in the air column as the tube is raised. So right now what is actually happening is something like this. Your tube is this open tube here. Okay, what you're doing is that you're gradually trying to raise the tube up. So over time, it will go up like this in a manner similar to this. I try to draw the diagram out. Over time, it is being raised. So if this one is your water level, it's gradually being raised up. Okay. So at the same time, you always have a loudspeaker that is producing sound waves. So what's happening here is that as you raise the tube up, you have a column here, highlighted in green here. So your sound waves will travel downwards. It hits the water surface, it gets reflected back, and then in principle, it should form a stationary wave. But I mentioned to you guys before, in practice, it doesn't form at all particular, at any frequency or any lengths. It will only form at certain frequencies or certain lengths. So right now, what is happening here is that as you raise your tube upwards, you're actually varying the length of the air column. This is the length of your air column. Okay, you're varying the length of your air column. So as you're varying the length of your air column, at certain lengths, your stationary wave will be formed. This one is a case where I mentioned to you guys before, where frequency remains constant, but length is varied. Okay, there was another variation to this I mentioned is length constant, but frequency varied, right? So this one is the other variation. Frequency constant, but length is varied. Okay, this is what's happening now. Notice that in your question, they never say anything about varying the frequency of the loudspeaker. They just say the frequency of the loudspeaker is 530 Hertz. Okay, so we know that as you go and as you raise the tube upwards, at certain lengths, you get stationary waves. The question is asking you, how do you detect those stationary waves without doing any additional, without bringing any additional equipment? So the easiest way to detect the formation of stationary waves, which happens to be sound waves here, is that you usually will be able to hear a much louder sound when stationary sound waves are formed. Okay, so this one doesn't need you to do any, to use any special equipment. You just hear using your ear. A much louder sound can be heard. Okay, right. So from here, they will give you some questions. Now, before we go to that, let me just draw for you the pattern of stationary waves that will be formed. If let's just say that I'm talking about the formation of my first stationary wave, second stationary wave, and even my third stationary wave, it will probably look something like this. Okay, it will probably look something like this. Let me just redraw this and draw the lines. It will look something like this. Okay. Now let me just draw this little line. You get something like this now. Okay. All right, this is your first, second, and third stationary wave. As you go and increase the length, it could be that this one is L1, L2, L3. Okay, so just bear this in mind first. And then I also always mention to you guys before to remember this. If it is close and it will always be a note. if it is open end, sorry, if it is open end, it will always be an empty node. That's what you're seeing over here, where you always see empty node and node. Okay, that's what you're seeing here. Now, if you read question B, they tell you determine the height of the top end of the tube above the water surface, above the surface of the water when a stationary wave is first produced in the tube. Okay. What is the height at the top end of the tube above the water surface when a stationary wave is first produced in the tube? Assuming that an antinode is formed level with the top of the tube. So what you can basically do from here is that you can try to visualize the formation of the first stationary wave. They already ask you to use the first stationary wave that is formed. If this is your water surface, your air column is this length here. Okay, your first stationary wave that will be formed is one which has antinode at the top, node at the bottom. So this is your shape. This is your first stationary wave. So they want the height from the top of the tube to the surface of the water. You will see it's actually talking about this. This is the height they want from the top end of the tube to the water surface. So at the same time, you will notice that this is actually from antinode to node. It's the antinode to node distance, which is by right lambda over 4. But you have an issue here right now in the sense that you do not know what is lambda. So you have to use another separate equation to find out what is lambda. We already know the speed and frequency of the sound wave, 530 hertz and 200 and 340 meter per second. So we use v equals to f lambda, 340 equals to 530 times lambda. Lambda is 0.641 meter. So now we can proceed to find out what is h. H is lambda over 4 is 0.641 divided by 4, giving us 0.16 meter. And there we have it. Okay, so this one is okay. To do this question, you need to know how to draw the pattern of the stationary wave. You need to visualize it a little. Okay. Okay, then other than that, we can move on to part C. All right. So part C is asking you, find out the distance moved by the tube between the positions at which the first and second stationary waves are formed. What is the distance moved by the tube between the first and second stationary wave? So this one, again, it will help if you were to draw out the pattern of the stationary wave. Okay, so if I know that this one is the first formation of stationary wave, which looks like this, and then I know that this is the second formation of my stationary wave, which looks like this. I want to find out the distance that has been moved by the tube between these two. Okay, now if you want to find the distance that has been moved between these two, you can actually just pick a reference point. If let's just say I pick the top end of my tube as my reference point, this distance here is the distance moved. Okay, they just say distance moved by the tube, right? So you pick some sort of reference point, you make sure you use the same reference point. If I pick the top end of the tube, the distance that has been moved by the top end of the tube is actually the distance moved by the tube itself. Okay, so I want to find this distance moved. All right, so how do I go about doing that? If you try to draw your tubes to scale, this one you can see is something like this. Okay, probably no need to draw to scale. You see, if I talk about this shape here, from the water surface, which is the orange line here, this one would be lambda over 4. This one is for the first stationary wave. If you go on to the second stationary wave, from the water surface to the top end of the tube, this one is going to be 3 lambda over 4. Okay, because I know that this one is lambda over 4, this one is lambda over 4, this one is lambda over 4. Distance between adjacent nodes and empty nodes will always be equals to a quarter lambda. Okay, so now I know this one in total is 3/4 lambda. You see, if I take this distance minus of this distance, I'm gonna get this distance. So the answer would just be 3/4 lambda minus a quarter lambda, giving me half lambda. And I already know that lambda is 0.64. So divided by 2, I'm gonna get 0.32 meter. I got it at 0.641 now. You can actually just round it out if you wanted to. If you don't want to round out, you want to use 0.641, it's also fine. You will get back the same answer. Okay? Right, so this one is how you do this question. So that one is okay. Then I move on to the next part. Next part should be DC circuits or current or electricity reading. Okay, so let's move on to the next part, question 6. We still have 2 questions. We should be able to finish it today. Okay, now you have a cell of EMF 0.4 volts that's connected to a metal wire as shown in figure 6.1. Your cell has internal resistance. The current in the cell is 0.8 amps. Wire X has length of 3 meter, cross-sectional area 1.3 times 10 power minus 7 meter square, and a resistance of 0.4 ohms. Calculate the charge passing through the cell in a time of 7.5 minutes. Okay, so here they tell you current in the cell is 0.8 amps. We know that you're going to have a current of 0.8 amps. This current will move through your cell like this, move through your circuit like this. So you want the charge passing through the cell in a time of 0.75 minutes. You use current is rate of flow of charge. Current is 0.8. Your time is 7.5 minutes. Remember to change it to seconds, so it's 7.5 times 60. Eventually, you will get your Q as 360 coulombs. Just like that. All right. So this one shouldn't be any big issue. Okay, then the next one they'll ask you to find is this. Find out the percentage efficiency with which the cell supplies power to wire X. So in our case here, if you're talking about the percentage efficiency, you want to find out the percentage efficiency, you can actually think about it as this. The percentage efficiency is power dissipated in X over power provided by the cell. Okay, I think this one they call it cell, right? Not battery. So power provided by cell times 100%. This one you can think of it as your output power. This one could be thought of as your input power. All right. So find out the power of your cell first. Power of cell is EI. This is pretty standard. Okay. Take your EMF, multiply with your current, 0.384. Then after that, find out your power dissipated by your wire X. It's I squared R. Because here, the easy way to do it would be to use your resistance and the current. All right. P is I squared R. 0.8 squared times 0.4, giving you 0.256 watts. So therefore, your percentage efficiency will be px over p cell times 100%. Then after that, summing the values, you're going to get the answer as 66.7%. Just like that. Okay, so nothing really that difficult for this one. Okay, then after that, we go on to part C. Now, there are 3.2 times 10 power 22 free conduction electrons contained in the volume of wire X. For wire X, calculate the number density N of the free electrons. This one I think shouldn't be that difficult. You just need to know what's the definition of number density. Number density is the number of free electrons per unit volume. So they already tell you your number of free electrons. This one is your N. To find your volume, because this is a wire, which we assume has circular cross-sectional area, so it's therefore a cylinder. If this one is length L, and this one is cross-sectional area A, volume is therefore AL. Okay. So based on this definition, number density is number of free electrons divided by volume. It is the same as N divided by AL. So you know all these values already. N is 3.2 times 10 power 22, cross-sectional area is 1.3 times 10 power minus 7, and the length is 3 meters. You can get these values from the previous page. Okay, it's over here and over here. Okay, so eventually you will get your answer. You will get your answer as 8.21 times 10 power 28. Just like that. And then after that, the next part of the question will ask you to find out your average drift speed. In your entire AA syllabus, there's only one thing that has drift speed. There's only one equation that has drift speed. That one is this one. A is equals to AN QV. This is the only equation in your AA syllabus that has drift speed inside. So you see, the moment you see the term drift speed, just use this equation. Okay, so you know everything from here. Also, you want the drift speed, which is this one. So sum in everything else. Current is 0.8. Error is 1.3 times 10 power minus 7. Number density is what you found here. Charge of an electron is 1.6 times 10 power minus 19. You will eventually get the answer as 4.68 times 10 power minus 4 meter per second. Just like this. Alright. Okay, so this one nothing that difficult. Alright, then we go on to the last part, which is your state and explain question. Right, so I'll clear off everything here. Okay, now from here, we tell you a wire Y with the same cross-sectional area as X and made of the same metal. Wire Y is longer than wire X. Wire X is now replaced with wire Y. Assume that Y has the same temperature as wire X. State and explain whether the drift speed of free electrons in wire Y will be greater than, the same as, or less than that in wire X. So what do we have here is something like this. Let me just redraw the diagram here for easy reference. You have this with internal resistance, and then you have the wire like this. Okay, so we know that this is 0.48 volts. We know this is 0.48 volts. This one is internal resistance R. Okay, so right now they want you to find out whether the drift speed of free electrons in the new wire is going to be greater. Originally, this one was wire X, but then we changed to wire Y. Okay, so what's going to happen to the drift speed? Right, so what we know here is that wire Y has same cross-sectional area and same metal. So the moment we know that X and Y are made of the same metal, we know they're going to have the same number density. Okay, and then YY is longer than YX. So in our case, we use this equation. R is equals to rho L over A. We know A is the same, rho is the same. Yeah, this one also can be, yeah, this one I say same number density. You can also say it's same resistivity. Okay, both are also, it implies the same thing, okay? Same number density, same resistivity also. So rho and A constant would mean that R is proportional to L. So from here, if I know that L is longer, that means R is longer, R is larger. Okay, so this one is okay. Now it's from here that I can actually make some other conclusion. So if my L is longer for YOY, this one is I'm talking about for YOY. Okay, if my L is longer, my R is bigger. So what this means is that my total resistance increases. I can actually just say that maybe I just make a shortcut here. If my R increase, my current drops. Okay, L increase, current drop. My current drop, therefore, my drift speed would be lesser. This one I need to use I is equals to A N QV. So in my case, A N and Q constant, therefore I is proportional to V. Okay. There's another relation here that you need to know. I is equals to A N Q V. Same cross-sectional area, same number density, same charge of electron. So I is proportional to V. So in my case, if current I drops, V would drop. Therefore, my drift speed will be less. This is the wording for the answer. R is rho L over A, rho and A constant are proportional to L. Since Y is longer, it has larger resistance. This means that a smaller current will flow through Y. And then I use a separate equation. I is A N Q V, A N and Q constant, I is proportional to V. Since a smaller current now flows through Y, the drift speed is therefore lesser. Okay. This one is worth 3 marks. So you need to explain quite a fair bit. All right. Okay, then we go on to the last question. That one will be on particle physics. Okay, so this one is okay. Then I move on to the next one, which is 7. Okay, now the first part actually relates to your dynamics chapter, conservation of momentum. So let's go through this one first. Right, we tell you have a stationary nucleus P of mass 243U that decays by emitting an alpha particle of mass 4U to form a different nucleus Q. The initial speed of the alpha particle is 1.6 times 10 power minus 7, 10 power 7 meter per second. The next thing they ask you here is this. Using the principle of conservation of momentum, explain why the initial velocities of Q and alpha particle must be in opposite directions in the first place. Okay, so right now you are supposed to use conservation of momentum. You can think of this one as before and after. In our case, momentum, last time you learn it as before and after collision, but this time you think of it as something similar. Before and after decay is the same thing also. Right now, what's important to know is that this thing is stationary. Okay, That means your V is 0, your momentum is 0. When you're talking about conservation of momentum, the thing that comes into mind is that the sum of your initial momentum must be the same as the sum of your final momentum. Okay, so this one here, you should have been able to recognize that since this one is stationary, the velocity is 0, the momentum is 0, and it's the only thing there, your initial momentum, the sum of it is 0. So by conservation of momentum, the sum of your final momentum after the decay must also be 0. And that is what you will be able to see here. Okay, initial momentum is 0, final momentum is also 0. But then you notice that right now, after your decay, P actually split up into two different things. You have nucleus Q and you have your alpha particle. This alpha particle has a certain speed and a certain mass. It therefore has momentum going in this direction. So your nucleus Q also has a certain mass. It now has also a certain speed. Its momentum is in this direction. This one PQ, okay? So right now, I know that PQ, if I'm talking about the sum of the final momentum, I mean, just by looking at this now, without looking at any equation in the first place, this is one momentum, this one is one momentum, but these two add up must be equal to 0. So it will follow that just by looking at this, PQ is equal and opposite to P alpha. The momentum of nucleus Q is equal and opposite to momentum of my alpha particle. Okay, but you want to prove it out using equation, you can do that. This one is just by you doing something like this, where you say that sum of final momentum is 0. So in my case, I will say that P alpha plus with negative PQ is 0. Therefore, P alpha is the same as PQ. If you assume going towards the right as positive, so PQ will be negative. You're still going to get the same conclusion. All right. So how do you explain this? You will have to say that total momentum before decay was 0. Your total momentum after decay must also be 0. So in that case, your alpha particle and Q must have momenta in the opposite direction. They must have equal momenta in opposite directions. Now it's because they have momentum in opposite directions in the first place that your velocities will be in opposite directions. That was the conclusion here. Okay, so that one is okay. This is conservation of momentum. Okay, then after that they ask you, find out the initial speed v of nucleus Q. They're asking you to find this particular v. All right. So in our case, we already know that the momentum of Q and alpha must be equal and opposite. I know that PQ is equals to P alpha. So from here, you apply the equation for momentum where we know that momentum is mv. So mass of Q times velocity Q equals to mass of alpha times velocity alpha. It will be 239U times V equals to 4U times 1.6 times 10 power 7. Okay, the alpha particle part, I don't think you have any problems because the mass is stated and the speed is stated. In the diagram, they already stated for you. 4U and 1.6 times 10 power minus 10 power 7 meter per second. But then for nucleus Q, the problem comes when they didn't tell you the mass. You see, they never told you the mass. You are supposed to know how to deduce out the mass. just by what they told you initially. If you consider the reaction that is occurring right now, nucleus P with mass of 243U has an unknown proton number of Z. I think I mentioned this before. If you have watched the recorded lesson for nuclear physics, I mentioned this before. Mass of a nucleus is actually the same as your nucleon number times with U. Okay. So right now, I know the mass is 243U. That means I have 243 nucleons. Despite here, my P, I know the nucleon number is 243. Because the mass was 243U, it means I'm taking 243 nucleon multiplied with the average mass of one nucleon to give me my mass of nucleus. Okay, so I know this one is going to give me 243 nucleon number, but proton number I do not know. Okay, so that one we don't know. That one is not an issue. We just give it some random variable Z. From here, your nucleus P will decay to become nucleus Q while emitting alpha particle. So here I know there's Q and alpha particle. What I want to do is that I want to balance off the proton number and nucleon number to get the nucleon number of Q and the proton number of Q. So this one will just be 2, 4, 3 minus 4. This one will just be Z minus 2. Okay. So eventually I will get the nucleon number as 239. My mass of Q is therefore 239U. Okay. That's why I can put it here as 239U. Even though the question never stated it can be deduced from the question, from the information given inside the question. All right, so even though you do not know the proton number here, that one is not an issue. We are not even interested in this, so don't bother about that, okay? We are only really interested in the nucleon number so we can get the mass of the nucleus. So this one is 239U times V equals to 4U times 1.6 times 10 power 7. Eventually, we will get the answer as V equals to 2.68 times 10 power 5. Okay. So that one is okay. So no issues. Then I'll clear this one off. All right, then the last thing we'll do, another thing here will be calculate the initial kinetic energy in mega EV of alpha particle. This one I already mentioned before. Alicia did ask this before. This one 1 EV is 1.6 times 10 power minus 19 joules. 1 mega EV is 10 power 6 times 1.6 times 10 power minus 19 joules. Okay, so they just found the initial kinetic energy in mega EV of alpha particle. K is half mv square. You know the mass as 4U. You know the speed as 1.6 times 10 power 7. Just sub everything in. The uniform atomic mass value, you can get it from the second page of your question paper. It is 1.66 times 10 power minus 27. Okay, so just get that value. You're going to get the answer as 8.5 times 10 power minus 13 joules. From here, you change to joule to EV. You divide by 1.6 times 10 power minus 19 to get EV. And then after that, from EV, you just change to mega. Eventually, you get the answer as 5.31 mega EV. Okay, so this one, no issue. 3 marks just for this. Okay, then the last page, we go to the last page. You have a graph of number of neutrons N against proton number Z. Okay, so bear in mind, this one is number of neutrons versus proton number. This is not nucleon number because there's a tendency for people to think that this was nucleon number. This is number of neutrons. So now, right now, they tell you that the graph shows a cross that represents nucleus P, which is this part here. Nucleus R has nuclear number of 242 and is an isotope of nucleus P. Nucleus R decays by emitting a beta minus particle to form a different nucleus S. On the figures that you have, draw a cross to represent nucleus R, label it R, draw a cross to represent nucleus S and label it S. Okay, so let's work with what we have. Nucleus P is having a proton number of 95, but a nuclear number of 148 plus 95. Okay, so giving us 243. Okay, now nucleus R has nuclear number 242 and is an isotope of nucleus P. Right, so nucleus P, we know that isotopes have same number of protons but different number of neutrons, right? Okay, so right now, since we know that R is an isotope of P, its proton number must therefore be 95. So this one I know is this. So this one is R, right? Nucleus R, sorry, I labeled this wrongly. This one is nucleus R. So I know that R is isotope of Q. So R is isotope of P. Therefore, proton number is 95. Okay, so that's what I know. And then after that, from here, I know that nuclear number of R was already given as 242. This is given. So from here, what is my number of neutron? This one will be 242 minus 95, giving me 147. So right now my R will be here at 95 and 147. This is nucleus R. And then after that, nucleus R decays by beta minus particle emission to give me nucleus S. What you can do is R is 24295 decays to become nucleus S plus beta minus particle. So all you just need to do is to balance off your proton number, nuclear number. This one will be 96 because it's 95 minus -1. This one will be 242 because it's 242 minus 0. So therefore, S, yeah, so this is your S already. S is going to be 24296. So what you want to find again is number of neutrons, which is 242 minus 96, giving you 146. So nucleus S will be here, where you have proton number 96 and neutron number 146. Just like that. Okay, so last question here would be just this one. State the name of the other lepton in addition to your beta minus particle that is emitted during the decay of your nucleus R. So this one by right, if you know what is, if you remember beta minus decay, maybe I just write it here to make things simple. If you remember your beta minus decay from particle physics, this one is neutron decay to proton plus beta minus particle plus electron antineutrino. So what is the other lepton? There are actually two leptons here. These are your two leptons. Okay, so this other lepton is what you want. This one is your electron anti-neutrino. Okay, so just like that. Okay, so with this, we're done with one paper.